we are at UW, and we have a race. I'm excited here. Let's go. Sunday AI for Robotics class. I wanted to go over a few topics here, no pun intended. And number one is the Intel RealSense camera, and then we'll review the ROS, logging into the VAR instance that we created. It's like an ISO file in Ubuntu 16.04 Melodic. But let's go over the camera sensors first. What I want to show you guys here is the depth stream information. So you can kind of see this is what your robotic car is going to see. We're going to be pulling a lot of this information off via topics, and this is actually a node within the system that is publishing information to other subscribers. We'll go over that soon. But what I wanted to show you guys here is the accelerometer streams and gyroscope streams that we talked about, the X, Y, and Z. This information is being pulled off that 6-axis inertial measurement unit. So it understands where it is in space, the yaw, the pitch, and the roll, and all that information. But also the color stream information, the RGB, is going to be advantageous for us later as we start to integrate machine learning algorithms in TensorFlow 2.0 for navigation and planning. So it knows, all right, that's a red piece of paper, that's a blue piece of paper, that's a yellow piece of paper. I want to find the blue one, keep going, keep moving on. We'll get into that later. So just this is a very quick... Good afternoon, AI for Robotics class. I wanted to address just a few questions that we have going in to our next lab. And number one, what are the frames on a robot? Are they X, Y, and Z versus, quaternions? We've been doing these transformations here for a couple of weeks, and we haven't really defined each individual frame on a robot. So let's take a look at the point cloud that you guys will see all the way over on this side. And I'm using the Azure Microsoft Kinect sensor. So if you take a look at this, the frames, and above me here, you'll actually see a view frames command pulled from ROS. That is running the race car simulation. And each individual one of these, from the SimPose and the base of the car, the camera length, the base footprint, the left wheel, the right wheel, every single one of them will have a reference point, right? So you have a Z, an X, and a Y. And these are kind of like those angles on Euler angles, each one, but in ROS, it only deals in radians and quaternions. And there's a significant difference. For us, Euler angles are more understandable, and it's a good reference for decomposing rotations into individual degrees of freedom, like for kinematic joints on robots, just like you see here on my body with a base link and a bunch of individual links. But they had significant disadvantages when it comes to computation in computers, mostly on ambiguity and we call it the gimbal lock. So as the pitch approaches 90 degrees theta around, you'll end up seeing that it'll fail. And quaternions essentially is a 4-element vector which can be used to encode any rotation in the 3D coordinate space, and it has those advantages. So I like to visualize a quaternion. There's a couple famous YouTube videos where you're curling your fingers inwards. The IJK, these imaginary dimensions that are run parallel, 90 degrees orthogonal to each other, allow us to understand and compose this one real element and then these three complex elements. So we further understand how these rotations are occurring, but we have to constantly transform these inside our code from quaternion to Euler angle and vice versa all the way back.
Linear dynamic model and feedback control final project presentation in a spatial computer here. What you guys can see is I'm just showing the example of a robot that can see and understand its surroundings. It has spatial awareness. The MinSeg is not that. And what we're focusing on here generally first is just looking at the dynamic model and the feedback control mechanisms. And then there we go. Awesome. I'm just playing in the background a little bit. works out pretty well, actually. Let's bring it a little closer. So you can actually read it fairly well.
This guy can really go. 3, 2, 1. Go ahead. It's going to come back. Here we go. Follow that line, buddy. This is tricky. Oh, you're gonna come the other way? Oh, you don't want to go that way? You want to turn? That's cool. I don't tell robots what to do. Eventually, you're gonna be telling us what to do.
Open source platform here using a Raspberry Pi 4B. And I have a Top Hat board. I have an Intel SR305, and I also have an Intel T265, which is the tracking module. And that's what I wanted to show you here. You can use that tracking module for, so as you can kind of see, it goes in circles as the car would go around a certain type of track. If you're using a convolutional neural net via perceptrons, some kind of machine learning algorithm to train the system with a neural net to go over and over and over again with certain types of tracking algorithms around a predetermined track, you can use this to track the error deviation of the motors, of the system, of the servos, of the control system, all of the sensors and the feedback loops. And it's really unbelievably helpful to program autonomous machines in this manner. And again, this sensor is only about $200. So you can, and this kit's about $100. So you've taken a very low price, low cost kit, and made it sophisticated. And that's what we want to do. We want to uplift these type of systems, versus some of the more unbelievably expensive. You need like a 6 or 9 axis inertial measurement unit to get the yaw, pitch, and roll from the robot. But you can use this information and feed it back into the control, perception engine to actually send signals to the motor, send signals to the servo, and then feed it back into the sensor system. So we can go along each one of these axes. And the T265 also provides, linear velocity, angular momentum, and this information is very useful as long as you know how to use it and where to apply it. But
Hello, good morning, University of Washington, EEP 598 for project management. We have a first assignment here. Again, University of Washington, EEP 598 for project management. This is for Team 8. Hello, good afternoon, University of Washington, EEP 598. This is for homework 2 for Team. Again, University of Washington, EEP 598. This is for homework 3, Team. Good afternoon, University of Washington, EEP 598 project management. Team 13, this is for our final project. And primarily what we're going to be doing here is looking at emerging technologies and how different types of project management principles and volumetric capture. Here you're seeing telepresence using 3D avatars captured via vertical cavity surface emitting lasers or time-of-flight sensors implemented with an AI machine learning algorithm so you can actually see my face, and then it's using the Azure V4 the depth camera on the front to actually track my hands and the movement in real time.
all right, multi-cam example here. Here's a nice point cloud. Kind of see that to the left-hand side of the screen. Really, really cool.